Most companies believe the cost of artificial intelligence is paid upfront. It is not. The real cost begins after deployment, when intelligence starts running continuously inside the enterprise. Training is a capital event. Inference is a recurring obligation. And at scale, inference behaves less like software and more like a utility bill that compounds with every customer interaction. The question is not whether AI works. The question is whether its inference cost structure improves your margins or silently rewrites them. In the early stages of adoption, executives focus on model training costs. The headlines encourage this instinct. Billions spent on accelerators, large-scale data centers, foundation model development measured in capital expenditure. But for most firms, training is not the enduring economic variable. Inference is. Training forms the asset. Inference activates it. And activation is where cost behavior becomes permanent. Every time a model generates a response, ranks a product, flags a transaction, routes a shipment, summarizes a contract, or assists an employee, inference occurs. At small volumes, the cost appears trivial, fractions of a cent per request. But when AI becomes embedded across customer service systems, underwriting engines, logistics coordination, personalization layers, compliance screening, and internal productivity tools, inference stops being episodic. It becomes continuous. Continuous systems behave economically like infrastructure, not like features. The cost structure can be reduced to a simple chain. Infrastructure enables compute usage. Compute usage determines marginal inference cost. Marginal cost multiplied by volume determines economic outcome. Infrastructure to compute to marginal cost to volume. This sequence defines whether AI produces operating leverage or recurring margin pressure. The popular claim that AI delivers near zero marginal cost is directionally appealing but economically incomplete. Inference consumes accelerator time, memory allocation, networking capacity, redundancy provisioning, monitoring systems, cooling infrastructure, and energy. Each call may appear inexpensive, but large-scale deployment multiplies that micro cost relentlessly. At millions of daily inferences, even fractional pricing changes become material line items. Scale converts microscopic unit cost into macro-level financial exposure. Traditional labor scales roughly linearly. Double transaction volume and staffing typically rises in proportion. Inference shifts the scaling variable from wages to silicon. The marginal unit of production becomes GPU cycles rather than employee hours. Labor-driven variability is replaced with compute-driven variability. This alters operating leverage fundamentally. AI-intensive firms therefore resemble capital-heavy industries. They carry high fixed or semi-fixed infrastructure costs paired with relatively low marginal inference costs. Once capacity is provisioned, additional usage is inexpensive, provided utilization is high. If demand expands faster than infrastructure investment, margins widen quickly. If demand stagnates while infrastructure remains provisioned, cost rigidity erodes return on capital. Utilization rate becomes the silent governor of profitability. The economics also differ depending on deployment context. Internal inference systems, coding assistants, analytics co-pilots, automation engines generate cost leverage. Their economic test is whether inference costs less than the labor it augments. External inference systems, recommendation engines, conversational interfaces, personalization frameworks generate revenue leverage. Their test is whether inference costs less than the incremental revenue or retention it produces. Confusing these two categories distorts capital allocation discipline. As inference scales, a deeper structural issue emerges in the utility consumption model. Many firms outsource inference through cloud providers or API-based model access, reducing upfront capital expenditure while introducing vendor dependency and variable billing exposure. At this point, we must account for what can be described as an infrastructure royalty. If the firm does not control the silicon, fabrication, or data center layer, a portion of every customer interaction effectively flows upward to the hardware substrate. Margin leaks toward the chip designers, the fabrication plants, and the hyperscale cloud operators. The enterprise assumes customer acquisition cost, revenue volatility, and competitive pressure, while the infrastructure provider captures relatively stable compute margin. In extreme cases, the firm becomes a pass-through entity, converting its own operating revenue into dividends for the silicon layer. This is the inference tax, vendor sovereignty expressed as structural margin extraction. Inference economics are also shaped by competitive escalation. As AI adoption spreads, expectations of quality rise. Firms respond by deploying larger and more complex models to maintain parity. Larger models are heavier models, more parameters, greater memory demand, higher compute intensity per request. The economic question becomes whether quality improvements justify incremental inference cost. Here, the model inflation trap appears. If competitors upgrade to heavier models, the baseline for acceptable intelligence rises. Others are forced to follow simply to defend position. This produces computational inflation. Firms spend more compute merely to maintain the same market standing. They run faster on the margin curve simply to remain stationary. Optimization therefore becomes a financial strategy. Quantization, distillation, batching efficiency, model routing, and hardware specialization are not merely engineering refinements. They are capital preservation mechanisms. A modest reduction in cost per inference compounds across millions of transactions. Efficiency gains stabilize gross margin. Engineering discipline becomes capital discipline. At significant scale, inference economics resemble industrial production systems. Capacity planning, throughput management, redundancy provisioning, depreciation schedules, and energy efficiency move to the center of financial analysis. The AI system is no longer a feature within the firm. It is a production plant. Its output is intelligence. Its input is compute. Its constraint is thermodynamics. As inference demand expands globally, it drives capital expenditure in semiconductor manufacturing, data center construction, cooling systems, and energy infrastructure. Inference is not abstract. The digital layer rests on mineral and energy foundations. Intelligence is thermodynamic. The inference plant requires continuous caloric intake in the form of electricity and cooling. Heat dissipation systems, water usage for cooling towers, and power redundancy infrastructure become material balance sheet considerations. These are not peripheral externalities. They are primary variable inputs of the new economy. To ignore the cooling tower is to ignore the gross margin. Over time, marginal inference cost tends to compress. Hardware improves, specialized accelerators increase efficiency, and optimization techniques mature. As cost declines, capabilities that once commanded premium pricing become baseline expectations. Differentiation migrates away from raw model power toward proprietary data, integration depth, distribution channels, and brand trust. The economic premium shifts. The life cycle follows a predictable arc. Initial scarcity and novelty create differentiation. Rapid scaling introduces capital intensity. Competitive escalation raises computational requirements. Optimization stabilizes cost. Widespread adoption compresses pricing power. Eventually, inference becomes background infrastructure, normalized, embedded, economically routine. The firms that succeed are not those that deploy the largest models indiscriminately. They are the ones that treat inference as a cost behavior system. They monitor utilization precisely. They manage marginal cost rigorously. They negotiate compute exposure strategically. They recognize where the inference tax accumulates and where computational inflation threatens stability. The governing structure remains constant. Infrastructure enables compute usage. Compute usage determines marginal inference cost. Marginal cost multiplied by volume defines economic outcome. When that chain is disciplined, inference becomes operating leverage. When it is ignored, inference becomes recurring margin pressure. At scale, artificial intelligence is not simply a technical capability. It is an industrial cost structure anchored in silicon, energy, and capital allocation discipline. And the economics of inference determine whether AI becomes a durable engine of profitability or a permanent line item that quietly reshapes the margin profile of the modern enterprise.